All right, guys, so the interest today was to solve these exponential equations. Now, how do I know that these are exponential equations? And I know these are because I have a variable in the exponent. So whenever I see a variable in the exponent, I need to kind of train my mind to look for a certain amount of patterns to make it more convenient for me to be able to solve these. Now, one of the first things that I always look for, because one is the easiest and a little more straightforward, is, okay, I have a variable in the exponent. Now, is there a way to rewrite my base equal to the exact same base on the other side? Because if I do, I could just set the exponents equal to each other and solve them. Now notice that my left side of my equation has a base of 2, my right side has 128, but I can rewrite 128 as a base of 2 because I know 2 raised to the 7 is the same thing as 128. So technically I haven't done anything mathematically different. I haven't really changed much other than just the way 128 looks like, which I just changed it to 2 raised to the 7. Now you can see here that I have a base of 2 that's equal to another base of 2. So that means that if this is to be true, my exponents have to be equal to each other. So I could really just draw out my bases and set 3x plus 5 equal to a positive 7. Now you notice that this becomes a very algebra 1 equation, and all you have to do is just solve for it. So if we minus 5 on both sides, we end up with 3x is equal to a positive 2. And then we divide by 3 on both sides, and we end up with x is equal to 2/3. So that's just pretty much it. Again, the key thing here is to remember that you are trying to rewrite your bases to be equal to each other to pretty much just concentrate on the exponents. Now, of course, this is one that's a little more straightforward. Number 2 is a little bit more challenging because I noticed on the left side I have a base of 5 raised to n minus 3, but then I have my 25 at the denominator. Now I can write 25 as a base of 5 pretty easily. Let me go ahead and do that. I end up with 1 over 5 squared, and then I can see here that, yeah, I do have 2 bases are technically the same, but one is in the fraction. So you got to remember your rules of exponents. All you have to do in order to make that base of 5 move to the numerator is to make the exponent negative. So we end up with 5 n minus 3 is equal to 5 to the negative 2, because remember, making that exponent negative, that action makes that base change sides of the fraction, so to speak. So remember that, and then you can see here that you have a base equal to a base. That means that n minus 3 is equal to a negative 2. Solving for this equation now, you end up with n is equal to a positive 1. And that is it. If you plug it in, you'll notice that it checks out perfectly. And that's it. And just to reiterate again, the key thing here is to make sure that this is your first attempt at solving these. When you see an exponential equation, see if you can rewrite the bases to be equal to each other, because you notice once you do, they're pretty straightforward. All you're really doing is solving that newly made equation that is usually not that hard. All right, so let's kind of review a little bit of this thing first. All right, guys, so my attempt here is to remind you guys exactly what an inverse is. Now, ignore these 2 problems here. This is literally just a side note. I'm even gonna put a little asterisk here to kind of tell you guys, hey, just take a break from what we are trying to cover with this exponential equations. And let's just remind ourselves, what does it mean to have an inverse, at least mathematically? So whenever you have an ordered pair or anything like that, let me show you what an ordered pair is. It's literally just an x and a y in these parentheses. Notice that your x value is an input, and then your y is the output. Let me go ahead and reverse that here. Set up input and output. So this is a function. You have some type of function. It could be an equation of some sort that when you plug in an x, you get a y out. Now, whenever you're dealing with inverses, an inverse is literally the reverse of that. What's going to happen what was once your inputs are now going to be your outputs. And what was once your outputs are now going to be your inputs. And usually you find a newly found equation that when you plug in your output, it will now become your input. So what it really does is it reverses your inputs and outputs, and that's why it's called an inverse. Now, of course, these things can get a little more complicated, but for the most part, that's exactly all an inverse is. That's all you really do. Now let's go ahead and apply this to what we were covering before. So if we have an equation y equals 2x, and I'm trying to fill out these tables, I know if I were to plug in a 0, anything raised to 0 is 1, so I know that my y value is 1. When I input a 0, I get a 1 out. Now, remembering my patterns within a table of exponentials, I know that every time I go up 1 in the y direction, I can multiply by my base, which in this situation is just a 2. And I can go ahead and do 1 times 2, which is 2, 2 times 2, which is 4. Working backwards, the opposite of multiplying by 2 is dividing by 2. So I end up with 1/2 and then 1/4. So graphing this guy here, I noticed that 1 or negative 2 and 1/4 would be right about there. Negative 1 and 1/2 would be a little bit above. 0 and 1 would be here. 1 and 2, and then 2 and 4 would be right over here. So I know it's never going to reach 0, but I'm going to try to get as close as possible to be a little bit accurate here. So that is my exponential equation. That is the table that represents it, and also the graph. Now, what we're going to start covering today is the inverse of this function. Now, just like we kind of went over a second ago, an inverse is literally just switching your inputs and outputs. Now, the nice thing that works that sometimes I feel like it shouldn't, but it actually does. If I have an equation, y is equal to 2 raised to the x, and I'm trying to find the inverse of that. Well, I know I'm going to be switching my x's to y's and my y's to x's. So if I'm going to try to graph that, all I have to literally do is change this y to an x, set equal to 2 raised to my x value, which is now going to be a y. So notice what I really did there is just took the inverse of it. I switched my x's and y's. Now, I could go ahead and start plugging in a bunch of values for 1 to figure out the y, but I already know what this function is. These are the input that gives me this output. So if I reversed everything, it's going to do exactly that. My mu x is now going to be a 1/2. If I were to plug in a 1/2, which was once my output, it is going to give me a -2. Because again, I'm inversing all my values, so they're switching. If I were to input a 1/2 now, it would give me a -1 out, and I could go ahead and do this for all my values. If I input a 1 now, it's going to give me a 0 because it's just working backwards. And now I can go ahead and graph these and see what I get out. Now I notice I have 1/2 and 4, which is, or 1/2 and -2. Roughly right about there. 1/2 and -1. And just like before, notice that when I go to my x values, they're getting cut in half and half and half. There is no way that I'm going to be able to get to 0. So I'm just going to go ahead and get it really close, but not exact. Then I know it's going to go on forever like this. All right, guys, so just as we mentioned, what we're covering today is a newly found function, and we're going to call that function a logarithm. Now, why did we give this a special name? Because they're actually really important and in a lot of different applicable mathematical situations. But in general, whenever you have an equation, or if we have y is equal to b raised to an x, aka an exponential equation, x equals b raised to the y is the inverse, and we call that inverse a logarithm. Now, this is the function that we're going to be studying. But one thing that you'll notice, and I'll write it over here to put a bigger emphasis, our newly found function is a newly formed one that's pretty tough to see. Notice that when we write equations, we usually like to rewrite them or write them as y equals. But notice that my y in this situation is an exponent. Logarithms are pretty much just exponents. But notice that how we currently have it is a really kind of not so friendly way of writing it. So that's why math people, like being the people they are going to come up with a whole new notation to pretty much rewrite it as y equals. Although we can't technically solve for these just yet, this y. Logarithms are based off just a nice way of rewriting exponentials or exponents that way. And the way that we write them is y is equal to log base b of x. And that's literally what they are. Some guy called it log. He says, okay, if I have a base, I'm gonna write it like little subscript in the bottom, and I'm gonna write my answer to what it is as x. So these two things are the exact same things. They're read as exactly the same. They are the exact same things. But we will go over a little bit more of like, how would I say, more exercises to help you see and train your eye to see the same thing here. Now, before we go on, keep in mind that this is a continuous function. Now, if we remember how the graph showed up in front, we know our domain are when our x values are greater than 0, and our range is all real numbers, because we can see here that these go forever, never in both directions. All right, guys, so just like we said, logs are really just fancy ways of writing certain exponents. And if logs are fancy ways of writing exponents, we can rewrite exponents as logarithms. And you'll notice that when we do these exercises, what always happens is, oh, we go over it, mathematically, the definition like we did above, they don't quite click, but you'll notice that once we put in numbers, they'll click a lot better. So notice here that we have a log. So when I have a log, and we call this log base 8, by the way, because the base is 8 of 1 is equal to 0, you need to train your mind to actually see an exponent there. Logs are exponents, exponents are logs. You just write them a little bit differently. Now, this is the way I like to think about them. If I read this as log base 8 of 1 is equal to 0, well, I know what my base is of this fancy exponent that's rewritten here in this log. And the exponent is always going to start with my base. My base in the situation is 8. Now notice that your log in general is an exponent. So whatever is equal to, that is what your base is getting raised to. That is what the exponent is. And it is going to be equal to whatever's in the inside of your log. So again, train your mind to see these patterns. Log base 8 of 1 is equal to 0. That means that this is the same thing as 8 raised to the 0 is equal to 1. Well, the way I've learned it too is they kind of showed this like kind of a circle. They show 8 raised to the 0 is equal to 1. Again, it doesn't really matter as long as you start training your mind to somehow see the connection between these two and know that these are exactly the same things. It's just a way of writing things. You'll be okay. If you were to rewrite log base 8 of 1 in your calculator, it will give you a 0 out because it's reading, okay, 8 raised to what exponent? 0 is equal to the inside. And you can see here that when I want you to do these, I also want you to double check them. So notice that 8 raised to 0 is 1. These check out. All right, guys, so notice in problem number 2 and 3 and 4, we have a log written. Now remember, logs are just really fancy exponents. So you need to be able to train your mind to see the exponent within the statement that's written. So if I look at this one, I notice I have log base 2 of 1 over 16 is equal to a negative 4. Well, that means that that number, that little subscript, that base is my base of my exponent. Now, whatever my log is equal to, remember, that is the actual exponent, which in this situation is a negative 4. And that base raised to that exponent is always going to equal the inside, which in this situation is 1 over 16. Now, again, this is a true statement that we started off with. If we were to double check this, what is 2 raised to the negative 4? Well, I know I cannot have negative exponents. So what I'm going to do here is just put this as 1 over 2 raised to the 4. Because if I move it to the denominator, all it does is change my exponent to a positive. Now 2 raised to the 4 is just 16. So you notice that it equals 1 over 16, which is equal to 1 over 16. This checks out. Now, if I look at number 3, notice I have log base 4 of 16 is equal to 2. Remember, log exponents. My base getting raised to whatever my log is equal to, in this situation is 2, is equal to the inside, which is 16. 4 squared is just 16, and you'll notice that 16 equals 16, it checks out. Now, noticing this other one right over here, I have a log base 3 of 1 over 27 is equal to a -3. My base raised to whatever my log is equal to, which is a -3, is equal to whatever I'm taking the log of, which is 1 over 27. Now, keep in mind here that I could have worked backwards. This is very similar to number 2. If I want to show that these two are equal, what I'm going to do is just rewrite them as bases of each other. So 3 raised to 3 is equal to 1 over 3 to the 3, because 3 raised to 3 is 27. Now, moving this base above, you end up with 3 raised to -3 is equal to 3 raised to -3. Remember, the action of moving that base makes it a positive. So not only do I want you to rewrite this as an exponential form, but I also want you to make sure that you're somehow showing that they're equal, either by the way I showed them in number 2 or number 4. Yeah. All right, so hopefully that gave you a little bit of a basis of how logarithms are exponentials. It's just the notation that you have to work on. But I want to make sure that you guys know how to work backwards too. So let's go from exponential to logarithm. So we're going to exponential logarithm. Notice that if we ever have some type of statement that involves an exponent, you can technically rewrite it as a logarithm and vice versa, just like we did above. Now, the way I like to do is like, okay, I know I can rewrite this statement as a log. Well, I know I have a log, a base of something. What's my base? What is getting raised to the exponent? In this situation, it's a 10. So that is your subscript. I'm going to write it as a little 10. I'll write it after my statement of a log. Now, remember that this is log base 10. Your log is always going to be equal to the exponent, which in this situation, my exponent is a 3. Now notice that whatever this equals is going to be whatever you're taking the log of. So you're taking the log of 1,000. So log base 10 of 1,000 is equal to 3. And again, don't always try to force yourself to always see it the way that I do. Of course, if there's something that clicks a little bit easier for you, go ahead and do that. Again, I always like to say, okay, log, what is getting raised was just 10. I always set it equal to whatever my exponent is, because I know my logs are just fancy exponents. And then what it's equal to is whatever you're really taking the log of. So log base 10 of 1,000 is 3. But look at number 2, again, log, well, base, well, what's my base? It's a 9. Now, what is this whole thing equal to? It's equal to a 3. So I know that I'm taking a log base 9. That is equal to my exponent because a log is an exponent. So those are 2 examples of pretty much how to think of things. Go ahead and try 3 and 4, and we will go over these in a quick second. All right, so let's go over number 3 again. Whenever you have a statement that is exponential, you can really write it as a logarithm one way or the other, because they are really just a different way of writing each other. So the way I like to do it is like, okay, I know I have a log. A log needs to have a base. The base in the situation is a 4. So there is my little subscript of a 4. Now, remember, you're taking the log base 4. Your log is equal to the exponent, because that's literally what a log is. Now, keep in mind that whatever your exponent is equal to is what you're taking the log of. So log base 4 of 64, and you can put it in parentheses to help you see it better if you want. That's what I usually do. Log base 4 of 64 is equal to 3. I always like to double check and see, okay, if I were to swing this around like I did in the exercise above, 3 raised to the, or 4 raised to the 3 needs to equal 64. That's exactly what my statement says above. Now let's go ahead and do 4. Log base, well, what's my base? What is getting raised to an exponent? It would be 125. Well, what is this exponential equal to? It's equal to a 5, which when I'm talking in terms of logs, it's going to be equal to an exponent, which in this situation, my exponent is a 1/3. So double check, my base raised to 1/3 is equal to 5. Okay. So hopefully with that exercise, I help you get a decent understanding of logarithms. Let's just go ahead and start evaluating logarithms by themselves. And you'll notice how hopefully this thing makes a connection of the above 2 exercises that we did. So they're asking me to evaluate the logarithmic expression. So notice this first one is telling me, okay, I want you to find log base 2 of 64. Now, if you were to type this in your calculator, it's going to give you a number, but I want you to be able to make the connection of what logs are really doing and what part of an exponential statement they're really trying to express. So the easiest way of doing this is to rewrite it as an exponential statement or an expression. Now notice I have log base 2 of 64. I don't know what that's equal to, but let's just call it it's equal to a y. Now it is at the beginning, it's kind of tough to see what it's asking for. So let's go ahead and change to exponential to hopefully make a connection. I am saying here, okay, I want to figure out what log base 2 of 64 is. It's equal to y. Now, if I were to change to exponential, I know I'm going to have a base of 2 raised to the y is going to be equal to whatever I'm taking the log of, which is 64. So notice what I did there is just change things a little bit. You need to train your mind, and you will with more practice, to see these two things, make a connection between these two. That log base 2 of 64 is really asking you to perform the following operation. Come up with an exponent that when you raise 2 to some exponent, it is equal to 64. Now, I think we could probably do this now. 2 raised to what is 64? What exponent? So 2, 4, 8, 16, 64. I believe it's 5. So this whole log base 2 of 64 is 5 because 2 raised to the 5 equals 64. And you can go ahead and do this for all of these. Notice you have log base 3 of 81. Now, of course, the point here is to understand the notation and to create shortcuts in a way. So if I'm taking log base 3 of 81, 3, my base, raised to what exponent is equal to 81? Anybody have that for me really quick? 3 raised to what equals 81, or can I do that? I think someone said 4. All right, awesome. Yeah, so log base 3 of 81 equals 4 because 3 raised to the 4 equals 81. 3 times 3 is 9, times 3 is 27, times 3 is 81. Now, if you look at the next one, log base 3 of 256, 4, my base, raised to what exponent is equal to 256? Anybody have that by any chance? Did anybody get 4 as well? I'm assuming so. So yeah, so 4 raised to the 4, I believe is 256 because 4 times 4 is 16. Times 4 would be 64, and then times 4 again would be 256. So you can see here that this whole log thing is raised to the 4. All right, so hopefully that helps you a little bit. You can see that we kind of try to just understand the notation. We did basic expressions, and now we're going to do basic logs. Now, logarithm equations are literally just equations with logs. Now, we are going to get to ones later where they have multiple logs, but we're starting with the basics. So let me show you what that means. We are solving an equation here. We want to find a value of n that when we take log base 8 of some value, it is equal to 1. Now, just like everything that if you ever try first at the beginning, you're not that quite confident. So make sure that if you're struggling to see what it's asking you for in log form, change it to exponential to see if it helps you understand what the problem is asking. Because all this equation is asking you is to find a value. Then when you raise 8 to the 1, it equals n. Now, if you can see that, go ahead, solve for it. But if you can't, change it to exponential. 8, my base, raised to the 1 needs to equal n. Now you can clearly see just by rewriting this in exponential, it's really straightforward. N is equal to 8 to the 1. 8 to the 1 is just 8. So you know that your n equals 8. So if you were to go back, if you were to plug in log base 8 of 8 in your calculator, it will give you a 1 out. You have found an n to make this logarithm true. Now let's go ahead and do number 2. Again, I always like to start with changing it to exponential because it just makes more sense. I have more experience with exponentials. 12 raised to the negative 1 needs to equal my n. N is equal to 12 to the negative 1. Now remember, you can never have a negative exponent in terms of a response. So let's go ahead and fix this. Let's move that base to the bottom of my fraction. The action moving it makes my exponent a positive. No need to write a 1. I'm going to place a little 1 on top of my numerator just to have my place value there. So n is equal to 112. Type it in your calculator, you'll be good. All right, so same thing for number 3, but a little bit more, kind of less, a little more to it. You have a base of 2 getting raised to the 3, n needs to equal x. You need to find a value of x that makes this equation true. So 2 raised to the 3 needs to equal 8x. Now you can see here that I am solving for x. Now I know what 2 to the 3 is, because 2 to the 3 is just 2 times 2 times 2, which equals 8, which will then be equal to 8x. Now solving for that x, if I divide by 8 on both sides, I can see that my x is equal to 1. So what value would make this statement true? It would be x equals 1.